Okay, hello guys. So let me check this recording. Share my screen. Good. Okay, so today we're gonna start with the real numbers. Okay, real numbers. And let me use. Okay. So and remember, I'm following the book by Edward Cogan. Okay. So this is. I'm gonna follow the order of the presentation. Almost all the books are the same, but some definitions are gonna take from there. And so I like how he established it. We assume the existence of a set R called the set of real numbers. That satisfies the following axioms. So the real numbers is an idea. Okay, it's not something we can see. We just create a new word. Okay, and this word is this one, that line. Okay, so that's our what we had created that universe called the real line, and we assume this universe exists, and it's called the real numbers. And in these real numbers, there are functions or operations, probably more than the functions. There are operations, maybe let's call it. Let's call it operations. And the first is adding, such that you take two real numbers, like x comma y, that's the notation for this, and this operation send it to another real number. So it takes a couple, so that's why we put this cross product like that, and it send it to a new number that we call x plus y. Okay, that's the one operation. And then there is another operation called multiplication, and it takes two real numbers and send it to another real number. And let's say we take a x and y, and it's send it to x times y. Okay, so there are two operations, and there is a relation it's called like this. So these are operations, and there is a relation on R such that for all x, y, z on the real numbers, we have first that if you want to add three numbers, you can add the first two numbers, or you can add the last two numbers. Okay, and if you're going to multiply three numbers, you can multiply the first two numbers, or you can multiply the last two numbers and then multiply it with the first number. Okay, it's called associativity, right? So we all know that. Then we know that you have two real numbers, you can add them, and it's commutative. The order of the adding doesn't matter. And the multiplication of the number, the order of the multiplication of the numbers, it doesn't matter either. It's commutative. Okay. And the third one is distributivity. And it's called, we have addition with multiplication. So this property says this is x times y plus x times c. Okay, these are properties really, we just did it, right? But it could be anything else. So when you work with programs, there are other kind of multiplications you create because it depends on the information you want, right? So for example, you have two matrices. Sometimes you multiply the matrices in different ways because the information that you need. Okay, so it's a relationship. But for the real number, this is the standard one. But what I want to say is that's not the unique. For some reason, we established that relation, and that's how we have been using. So, let me call this one, not just one. Let me call it action 1. Let me call it action 2. Let me call it action 3. So you don't forget this is an action. Let's call it action 4. If there is a unique element, zero in the real numbers, such that right, push the wrong one. Such that zero plus any x, right, equals x. This is for all x that is a real number. Sorry, I'm gonna take that thing out. For all x that is a real number. Okay. So you add 0 to any real number, you get the same real number. Okay, those are all this looks silly, but you know this is kind of why mathematics makes sense. We're creating a universe. Okay. And then there is for each x that is a real number, there is a unique y that is a real number, such that x plus y equals 0. And we write y equals minus x. Okay. So that's kind of the definition. So and actually there is a unique, but it doesn't say unique. Oh no, there is a unique, yeah. I should say here there is a unique. Because it's not, there are not more than one, okay? This is important. There exists, well, let's write it like, there exists a unique y such that this happens, the additive inverse, okay? Then we have axiom 6. there is a unique element. There is a unique element unit, or number one, says that the multiplication of any number with that one unit is the same. So there is a unique element one in the real number such that x times 1 equals x for all x that is a real number, and 0 different than 1. Action 7, for each x that is a real number with x different than 0, there is, and this is the inverse of the multiplication, there is a unique element y that is a real number such that x times 1 equals 1, and we write y equals x inverse, or y equals 1 over x. Okay. Action 8. So these are kind of the rules. Okay. So whatever is outside of this action, you have to prove it. Any other statement on the real numbers, you have to prove it. Okay. So these are basically our laws. So action 8, if x is less than a, implies x is less than y, implies x plus c less or equal than y plus c. You know, for x, y, c real numbers. So it means if you have an inequality, if you add the same number in both sides, it stays the same. Okay. And now this is transitivity for real numbers. Is x is less than y and y is less than c, this implies is like x less than c. Okay. Notice this statement, for example, right? So in all this statement, we're using the logic. So it's like P and Q implies R. Okay, this is P, this is Q, and this is R. And this is the implication. Okay. So all these terms, all these actions are written in the as a logic arguments. Okay, so we're consistent, we're being consistent with the first day of class. Okay. Action 10. For x and y real numbers, exactly one of the following is true. X is less than y is less than x, or x equals y. And then that's what you justify, that action justified our concept of a real line. Okay, because x, you choose x and y, So either X is less than Y or the opposite. Y is less than X. So in another position, maybe. Or they're the same. Okay, so it's a real line. So that action give us order. This give us order. Okay. It's different when you have R2. You have this point and then you have this point. Which point is bigger than the other one? Or even more difficult, I mean, which point is big? Which point is bigger? Which point is bigger? This one or this one? Or this one and this one? So A, B, C. So which one is bigger? A is bigger than B, B is bigger than A, C is bigger than A, or C is bigger than B. So you see it's complicated, but here is different. We have the real line and that's what people love it. Okay. That's the favorite play. And it's in astral algebra, they're gonna call it a field. We're gonna call it field. Okay. And this is the best set you can have. The real numbers are the best set you can have, okay? It's better than natural numbers, it's better than the rational numbers, it's better than the integers, it's better than the irrational, it's better complex numbers. Complex numbers are better because sometimes you can solve equations in the real numbers that you cannot solve the real number. In the complex numbers that you cannot solve the real numbers. But the complex numbers have complications. So in general, complex numbers and real numbers are the favorite ones, okay? They're called fields, okay? In astral algebra. And finally, our last action. If X is less than C and Z, sorry, if X is less than Y and Z is bigger than 0, this implies XC less than YC. So that means if you multiply the inequality by a positive number, the inequality stays the same. Okay. Okay, those are your actions. That's all that you know for the real numbers. So something that you didn't know is the next stuff. Okay. So this is probably something in calculus we never talk about. Okay. So you have seen things here like kind of many of these things are familiar, right? But here you go, new stuff. Probably things you haven't seen. So this list of properties assures that the system is an order field. Okay. All these actions assure us that the system is an order field. But we need more. I don't know if you guys can see the matrix. Will Smith, the bad guy, says more. Okay, we need more. So what we need? So we already said, okay, your real numbers is a line. Okay, you have numbers, one is bigger than the other one, etc. What else can we say? So we're gonna consider sets. And here is crazy. It's gonna be crazy what kind of sets you can. I mean, you can consider a set like this. We have talked about those intervals, right? That's a normal set, A, B, right? Another set is open set, open interval, closed interval, right? But there are crazy sets in the real numbers. So I could have like points, and points over here and points over here. That's a set. Okay. And what it's saying, something important here is a set S, subset of the real numbers, is set to be bounded from above or from below if there is a real number M such that for all X in that set, X is less or equal than the set if it's bounded, is less or equal than M, so it's bounded about, or any X is very equal than the M. Okay. So, for example, so let's say my set is all these points, all these points, all these points, all these points. So M over here, so let me write this green. Well, let's say that the green is 2 on these sets over here. Okay. So all those points are bounded below by some N1. Okay, look at. So none of these points are below than M1. And all these points are bounded above by M2. Okay. So this is definition, right? So bounded from above and bounded from below. So that's basically we have defined it. So definition, bounded from above, below. Doesn't mean the same. Above and below is totally different, right? But I don't want to write the whole definition again for below. So S is a subset of the real numbers. M is an upper bound or lower bound if for all X, for all S, if for all X in S is X is less or equal than M. Okay. So upper bound. So upper bound. So is it M is an upper bound for S if for all X that belongs to S, X is less or equal than M. And you know, even if it's lower bound, if X is better or equal than M. You have upper bound and you have a lower bound. Okay. And then, so you have a finite set. Let's say S is a finite. So you can find a maximum upper bound. Or you can, well, no maximum. So let's say you have all these points. So you have many M's, right? All these are M's. But if it's finite, you can choose the maximum. And that maximum is the least upper bound, meaning that point is the point that is bigger than all these points, but is less than all the other bounds, upper bounds, okay? This is called the maximum when the set is finite. And when you have a finite set, you can also talk about the minimum. Okay, so all this is good. You can talk about the minimum. Let's call it little m. Okay, if the set is finite. Now, then here the things start getting interesting, and there are interesting questions about this. Okay, this is something you didn't talk about calculus, and this is the beginning of analysis. Okay, this is gonna be the first word of analysis you're gonna have here, and it's called the least upper bound. Definition. The least upper bound. Definition, the least. A real number A is a least upper bound for S if A is an upper bound for S, having the property that if B is also an upper bound for S, then A is less or equal than B. Okay, so let's write it down. So it's what I said, right? Like I said it in words. I said verbally, right? Let's write it down since this is such an important definition. This is when you see that, when you're talking of the greatest upper bound, the greatest lower bound, then you know you are in analysis. You are not talking in calculus, because in calculus we don't talk about those things. So if A is an upper bound for S, having the property that if V is also an upper bound for S, then A is less or equal than B. So the same thing. So if V is a lower bound for S, having that property that if B is also a lower bound, then A is bigger or equal than B for lower one, right? Can I copy this? Let me see if I can copy this. I don't have to. Okay. Oh, come on, like this, right? Oh, it's making it bigger, smaller. Way to the left. Okay, no, that's not what I want. I want to copy it. I have to learn. I don't know. I don't know how to do this. Sorry. It was a try. So this is least upper bound, and then for greatest lower bound, I'm just gonna write it down again. So let's say I'm giving you time to catch up on the class, okay? Greatest lower bound. If S is bounded from below, okay, then a real number A is a lower bound. Let's see. Okay, if S is bounded from below, then a real number A that is a lower bound and for any other lower bound B, we have B less or equal than A, then A is a greatest lower bound for the set S. Okay. Okay, so we're gonna use the notation we're gonna say that we're gonna use lower upper bound, and we're gonna use the sub of the set S. Lower upper bound of S or the sub of S is the same notation. Okay? And then the greatest lower bound for S is equal to the inf of S. Okay? Or infimum. Okay? So, for example, if I have my set R, the real numbers, and I have points here, right? So if it's finite, I just can do finite sets, right? But if I have, this will be my supremum of S. So all these points are S, right? And this point will be my infimum of S. Okay. And that's something you only see in real analysis. So I think we're ready to do some proofs. So let me stop here this video of definitions. Sorry, it's kind of boring, all these definitions. But these greater and upper bound are really important. So we'll do some exercises from the book. So let's start doing exercises. So I'm gonna stop this just to make sure I don't make any mistake on recording. Then we continue.